Welcome back in our Stranger and Stranger series of different and inventive ways of doing science, astronomy in our case. Welcome back to my laundry room. And here we are with today's topic: neutron stars, quasars, black holes, pulsars, the bizarre stellar graveyard, where the giant stars go when they die. What happens to them? That's what we're going to focus on today. All right, so here's our topics: review of the HR diagram, and hopefully you've either finished that and turned it in which case I have it. I brought them home to grade. Your Stellar Lives gatefold, we were just barely working on that when everything changed. Stellar Lives, the Stellar Graveyard is what we address today. I'm going to quickly jump through that so we can keep the video brief. Hang on, and if you would please, pause the video now, go get your interactive notebook, your INB. If you don't have it already, grab it now, and we will go ahead and start. Pause if you need to right now. All right, looking at your table of contents, okay? We're into Chapter 3, and we're making really good progress through Chapter 3. Your table of contents has us past the HR diagram, Stellar Lives gatefold that you've been working on, and today we're going to cover all the information you need to fill page 58, 59, 60, and 61. Neutron stars, black holes. That's what we'll do today. All right. Moving forward with those topics, reminder that your HR diagram looks like this. Check Canvas for the details. The way to turn that in to me now, if you haven't turned it in yet, snap a picture, email that picture to me, and let me know, just in the email, that make sure your name is clear to me if it's not in your email title. I'll grade it, and I'll reply back with the grade that I've put in the system for you, and we'll stay on track this way. All right, so there's the HR diagram, and then afterwards, once you get it back, you'll put it into your book, opposite Sisters of the Sun. This one will be page 55 in your book. And then the gatefold that goes on the next page shows the lives of the stars. This is also in Canvas. Go ahead and browse Canvas to get to those requirements, and you'll be good to go. Let me know. Email me if you have any questions at all. All right. Let's talk about this place where the truly immense supergiants and hypergiants, where do they go when they run out of fuel? Where do they go to die? Check it out. It starts with the second, I suppose we could call it, the second heaviest object in the cosmos, neutron stars. And pulsars being a variety of neutron star, and magnetars, and they got other nicknames for other subgroups. But the idea is this collapsed core of a dead giant star is composed of nothing but neutrons. There's no protons or electrons left. They've been pulled down together and neutralized each other. Let's go through how that happens and how does that create an object? What does it look like? And, what can we expect? All right. So supergiants and hypergiants are how neutron stars got started. Okay, huge nebula condenses, creates these amazingly giant stars. Eventually, they, like all stars, run out of their fuel, and then they collapse. Before they collapse, they were probably between 10 and 30-ish masses of our sun. So you put 30 of our suns together, you've got a really heavy, star that's definitely going to form a neutron star. Heavier than that, it forms something else. We'll get to it. All right. So it collapses when it runs out of its fuel, because nuclear fusion in the core is no longer enough to hold back gravity. Okay, so it collapses in on itself, and that crush happens in a split second, and that shock wave reverberating through this giant star blasts itself back outward. So an implosion, explosion moment. And that implosion, explosion releases most of the star's material into this huge cloud in space. We call those nebulas, right? Giant planetary nebula, because eventually it'll form more stars and planets. And what's left is nowhere near as heavy as the star was before it collapsed. In fact, it's down to, it says here, 1.4 to 2.6 solar masses. Mathematics and physics and calculus, they've been able to calculate lighter than that, it wouldn't form a neutron star. It would collapse into like a white dwarf. Heavier than that, it's going to make a black hole. We'll get to that in a moment, like I said. But that star was rotating as it collapsed and reverberated outwards. What's left in the middle is still spinning. Check it out. So the size of these things, you could see compared to, they've set an example of one on top of a big city, neutron stars being there, quark stars being slightly more dense. The idea behind a quark star is that not just neutrons are what's left of the core of the gone supergiant or hypergiant, but it's crushed itself down to the parts of a neutron now, the quarks that made neutrons, and they are what makes up that entire massive object. So very strange objects indeed. These, we hardly ever see them. These are far more plentiful because they kind of show themselves to us. They reveal themselves. Let's see how. Now, they shine these beams out into space from their North Pole and their South Pole. And these beams are like lighthouse light beams that are shining out into the cosmos. Once in a while, one happens to point where we're looking, right? As it spins, it kind of winks at us. So I'm pointing at the camera. This actually is working pretty well. Pointing at the camera, and then the beam spins because it's a spinning object. And as it comes around, it points, and then it moves on, and then it points, and then it moves on. And it's blinking at us. Blink, 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 blink. Like really fast. Hundreds of times every second, this thing is blinking. And at first, astronomers were like, aliens! It's a sure sign of life. And then they realized, no, this is a natural, normal occurrence. Okay. And we discovered a new object. Tiny object. If you were to take a neutron star and drop it safely, somehow, here in the Salt Lake Valley, it would look like a pearl sitting in a, in its oyster shell. It'd be a pearl sitting in an oyster shell. That would be, if we were to drop it outside my window here, boom, and it's down, it's right here in the valley with us. Interesting. But if it happens to be slightly heavier than 3 solar masses, it's going to be something very different entirely. Let's consider the great white shark, the T-Rex of the cosmos. Ladies and gentlemen, a singularity, commonly called a black hole. Now we're covering information for page 60 and 61 in your book. Let's check it out together. Okay, so heavy star, once again, is the starting point. And when it collapses, but what remains behind is heavier than 3 of our suns worth, okay, it will continue collapsing. Not even neutron pushing against other neutrons will stop it. It will continue to collapse beyond that limit until it crushes itself completely out of existence. But if it doesn't exist anymore, how can it have a black hole? That's the strange bit. It still has its mass, its weight, its gravity, its overwhelming, irresistible gravity. But there's nothing there by way of volume. That's where we have strange relativity, all the laws of physics being seriously messed with. Okay, so it has mass, but it has no third dimension. It has no length, width, or height. It is a point, unimaginably heavy and indescribably tiny. That's a singularity. That's the heart of this thing. And all the mass swirling around it in this illustration are the things that are caught in its orbit, and they bump and jostle and crash into each other and make a big old mess and shed all kinds of light. Eventually their orbits decay and they fall into the middle, making it heavier and heavier. All right, so the singularity is the core. The event horizon, while it may look solid to us in the middle, looks like a solid sphere of darkness. There's nothing actually solid there. You can put your hands right through it somehow, if you could safely do that, right? There's nothing actually solid there to touch. It's simply the point where light can no longer escape. Now, the first one of these we've discovered. This is an illustration of Cygnus X1 and an invisible partner it danced with. Now this right here shed not just its beams of light out the top and the bottom, but X-rays. As these particles accelerated in their orbits to the speed of light, it kicked out a ton of X-rays into space. Those we were able to detect without them coming from this star. They were coming from near the star. That's really weird. And it also happens to be an incredibly bright object. Okay. So it's kicking out all these strange waves and radiation, magnetism, gravity waves shifting and rippling through space. Strange event going on here. That's how we found our first black hole. Here's a picture of Cygnus X1. It just looks like a bright star. Well, that's because all the light coming off of not only the blue star that it's stealing from, but the accretion disk itself at our distance, they blend together as a single, very bright light source. So it looks to our eyes just like a star, a bright star. But instead, it's kicking off all these extra X-rays and it's wobbling a little bit as it spins. That's how we found it. All right. Now, Hollywood suggests it looks like this, and for a long time, this is all we had to go off of was mathematicians predicting if this thing actually were to be close enough to see, what would it look like? So they created this imagery. And people weren't sure. They're like, it looks a little too sci-fi for me. And then we found we could actually get all the big telescopes in the world to cooperate to gather a huge amount of information from which we filter down to tiny little bits of information. Took years to build this image. And we have our first picture, no kidding, photograph of a black hole. Einstein, you were right. Calculus, you did it. Stephen Hawking, wish you could have seen this. Because you were right. That is a black hole. All right. Now, if we were to animate that picture, if we were to somehow fly around it from its original fuzzy image, right? But if NASA has done a simulation of what we're actually looking, it looks like a donut. Homer would be proud. He's like, man, that's a donut I could totally get into. And yet, take a look. What you're seeing is a single disk in orbit around the black hole. But as you're looking at it from one side, light from the other side is traveling up and it's being bent over the top of the event horizon to where you can see it. So we actually see light on the backside of this thing from where we happen to be looking, right? Crazy. And there it is. Okay. I have several videos I'm going to put down and come in the description below. I'd like you to watch them all. They really show you black holes and their sizes, what is a singularity, what's the event horizon, and it gets into a lot more detail than I was able to in my very brief video today. Questions, ask them below, and let me know your comments and ideas. This is very rudimentary. I'll try to, come up with something better for next time, but for now, this is what we've got. So go with it. Work on your interactive notebooks, and in the next couple days, watch for another video where I will take an example interactive notebook and show you how you can take your work, how to properly snap pictures of it, email them to me, we'll get your grades into the system, and stay on track through all this chaos. Stay amazing, keep going, look up at the stars once in a while, and hug on everybody around. Well, keep your social distance. Hug on them from a distance. Air fives. Woo! There it is. All right. Take care, friends. More to follow. And another picker card coming to you soon. Bye.